So far we have used the minimal coupling prescription to couple the gravitational field to other matter fields, a scalar field and an electromagnetic field. If we couple fields that we call generically in the context of gravity as matter, to differentiate it from gravity, to the gravitational field, these fields are acting as a source, and you expect that the variation of the term of the action of these fields that describe the coupling to the gravitational field with respect to the gravitational field will give the source of the gravitational field. Let me explain this a bit better. Typically, you will have, for instance, if you have a scalar field and you have a term, your action, now covariantized, of the form phi and j added to the rest of the action, what you find in general is that, so let's see, this j can depend on other fields or whatever. What you find is when you vary this term, you add to the equation of motion, okay, which was like this, multiplied by the square root of g, a term proportional to j, okay, that you can write in the right hand side of the equation. Instead of nabla square phi minus j equal to 0, you find something like this. So whatever couples appears multiplied, this is what means coupling in this jargon, comes multiplied by phi in the action, will appear as a source of the gravitational, in this case of the scalar field. Given some j, you can find what this phi is. In this case, it's a bit more complicated. We have general Lagrangian. Okay. That depends on phi, derivatives of phi, whatever, and the metric. But clearly, if I have some other term that describes the dynamics of the gravitational field, when I vary with respect to the gravitational field, okay, then I will get something which is equivalent to nabla squared of phi, and that describes the dynamics, and something which is the variation of this L with respect to g mu nu, that I can write instead of as a plus, I can put in the other side of the equation here, okay, and it will be something like this. Let me put it like this, not in a very rigorous way, but so that the idea is clear. So clearly this matter field acts as a source for the gravitational field, and we are interested in studying this source. The conclusion of what we are going to do is that this source is the energy momentum tensor, and we could have expected that because in a relativistic theory of gravity, it's not only matter that creates a gravitational field, but energy and everything and all the things that are included in the energy momentum tensor, because there is not just a vector or a scalar that describes this energy or matter plus energy density. We need a full tensor, and this is why the whole tensor has to act as a source. And we are going to see that this source or this term corresponds to the energy momentum tensor in the case of the scalar field. We will later generalize it to this result to the electromagnetic field. And okay, we are interested in the properties that this energy momentum tensor has. We have reviewed that it has to be conserved. It is conserved in the Minkowskian case, in the special relativistic case. So what happens in general? This is what we are about to find now. Okay, so we start with the action for a free scalar field. Well, covariantized, of course. Okay, and now we are interested in seeing what happens when we vary the action with respect to g mu nu. So we vary the action, but okay, let me make this explicit. Delta phi is equal to 0 here, because Okay, this would contribute if we vary the sorry, maybe I should say it. If I explicitly, so if I vary an action that depends on more than one field, well, I get terms which are proportional to the variations of each of the fields. I will get something like this. Okay, and this will contribute to the equations of motion of g mu, and this will be the equations of motion of phi. I am only interested in this part now, so I set d phi equal to 0, or in other words, I only vary with respect to g mu now. Okay, so see if this wants to disappear. So under this condition that delta phi is 0, then I have the following. I have d for x. I have to vary the square root of g, and then I have this term d phi squared, and then I have the square root of g, this 1/2, and the variation of the inverse metric, which is hidden inside of this d phi squared, d mu phi, d nu phi. Okay, now I need to know what this variation of the square root of the metric is. So let me do this calculation independently. Okay, first I take the variation with respect to the square root. So I get this 2 times 1 over 2 times the square root of g, and then the variation of the determinant. And now this is something that you can prove in different ways. The variation of the determinant, so this factor is still here, then the variation of the determinant is of this form, is the determinant times g mu and the variation with respect to g mu. Okay, and you can cancel partially this, and this gives you 1 over the square root of g mu delta g mu. Okay, as for the variation of the inverse metric, I mean, if considering that, assuming that we are varying with respect to g mu with indices down, the best way to do this is to consider this variation, the variation of delta mu, which is 0. Okay, because delta mu is always constant no matter what, but delta mu is just g mu alpha, g nu alpha. Okay, then I apply the Leibniz rule, and this is delta mu alpha g nu alpha plus g mu alpha delta g nu alpha. Okay, and this is equal to 0, so delta g mu alpha g nu alpha is equal to minus g mu alpha delta g nu alpha, and we can multiply this whole equation by g nu sigma, for instance, and we get delta g mu, and this gives me delta alpha sigma, so this is delta mu sigma equal to minus g mu alpha delta g, instead of nu alpha, let me write alpha nu g nu sigma, just to keep the order. Okay, this is the typical equation for matrices. This variation, so the variation of delta minus 1 is minus m minus 1 delta m minus 1, and this is the same for the matrix G alpha beta. Okay, this is one possibility. Okay, if we want to vary everything with respect to g mu with indices down, but you could say, okay, why not do it with respect to g with indices up? I mean, this is just a different variable, but we can do one or the other, and these two things should be related. Okay, in fact, they are related in this way. if you find the variation with respect to delta G alpha nu with indices down, you can construct the variation with respect to G with indices up. But here we have determined or we have written the variation of the square root of the metric with respect to delta of the metric, not the inverse metric. We can convert one into the other, and in this case the only thing is that the only difference is that you get a minus sign, okay, and you get G mu nu delta G mu nu. It is a bit simpler because you see that if we vary with respect to delta G alpha beta, we are going to get more terms here. So we just vary with respect to delta mu nu with indices up, and substituting all these results here, we get delta S is equal to the integral d for x minus a half square root of G mu nu delta G mu nu, and then we had 1/2 of d phi squared. Okay, this on one hand, and here we have plus a half delta G mu nu. I don't need to do anything. D phi, d mu phi, d mu phi. And I can take a common factor, delta G mu nu with indices up. Okay, and oh, sorry, I missed, I think, a square root of G here. Okay, so I can write it like this. And then I can write d mu phi with a half d mu phi minus 1/4 G mu nu d phi square. Okay, let me take also a factor of 1/2 here, so I simplify this a bit more. Okay, and this multiplied by delta G mu nu. So by definition, this whole thing is the variation of S with respect to delta G, with respect to G mu nu with indices up. And well, now you have to remember that when G mu nu was eta mu nu, this expression was minus the canonical energy momentum tensor, the energy of the scalar field, the one that we obtained as the conserved current associated to translations and so on. Okay, so let me write this in another language. If I multiply the result by 2 and divide by the square root of G, and then I have delta S, delta G mu nu. This is partial mu phi minus a half G mu nu d phi squared. And okay, what I have said before in words is that when G mu nu is eta mu nu, it was minus T mu nu. Let me call it canonical just to distinguish it in principle from the energy momentum tensor that we have obtained and that we are going to obtain by variant with respect to G mu nu. This result has been used to find an alternative definition of energy momentum tensor, not directly as the network current associated to translations. This is the Rosenfeld prescription to find for the energy momentum tensor. And the definition is, okay, compute the variation of the action with respect to G mu nu. Okay, if it is with G mu nu with indices up, I need this minus sign, and then set the metric equal to eta mu nu. And this could be the energy momentum tensor in Minkowski spacetime. And okay, in this particular case of the scalar field, we know that this energy momentum tensor, because it coincides with the canonical one, is conserved. So do we know that at least for this case, this equation is satisfied? Then we have two questions. Is this property true for when we consider other fields, or just for the, is it true only for the scalar field? And the other question is, well, if we do not set the metric equal to the Minkowski metric, and we consider this definition as a general definition in a general background, is this property still satisfied in some sense? Okay, so of course, since we are dealing with tensors, if we want to check this property, it only makes sense to check it using the covariant derivative. Okay, any other result, if I try to prove this for a general metric, so now we are taking a general mu, and if I try to do the same with the same partial derivative, then this will be a result that will depend on the particular set of coordinates that I am using, and I want a completely general result. So let me call this Rosenfeld, instead of Rosenfeld energy momentum tensor, the energy momentum tensor that one gets without imposing that the metric is the Minkowski metric. Okay, let me call it the gravitational energy momentum tensor. And now we want to check if this gravitational energy momentum tensor satisfies this property. Let us see what happens for the particular case of the scalar field, and then we will see if this remains, if what we find for the scalar field remains true for more general fields. Okay, so let us do this calculation. I use a minus sign because, well, it is simpler. We have minus, nabla mu, and this is partial mu phi, partial mu phi, minus a half of g mu nu partial phi squared. And I have to remind myself that this partial phi squared is always contains a metric inside, but it doesn't matter very much if we are using a metric compatible connection such as the Levi-Civita connection. And now we start computing, and first we find nabla squared phi, then there is another term, which is this one. Okay, and then minus a half, and this is just nabla phi of partial phi squared. Okay, this vanishes on shell. Okay, we know that the equation of motion is this. Okay, but remember that the conservation of the energy momentum tensor is only on shell, so this is on shell. Okay. And okay, let me operate a bit. Well, I have two partial derivatives of phi. This gives me a factor of 2, and what I get is two terms of this kind. Okay, phi and partial mu phi. These two terms cancel, and you see that the only difference between this term and this term, up to raising and lowering indices, is the position of the indices mu and nu, which is the opposite here and here. Okay, here is mu nu and here is nu mu, but we know the Ricci identity on scalars. This is 0 because in general it is only proportional to the torsion, and here with the Levi-Civita connection the torsion is 0. So these two terms are equal, and this is 0. Okay, so this is 0 on shell as well. Okay, this property is the general covariant generalization of this property here. Okay, and Well, we would be tempted of calling this conservation of the energy momentum tensor, because it formally looks more or less the same. But let me remind you that conservation means strictly this, whether you are in a curved or with a trivial metric or any other metric. It has to be this with a partial derivative. This for a current, so for something with only one index, this is the same as, I divide by square root of g, and here I multiply and divide. Okay, and this is the same as this. Okay, so if I have a covariant conservation law like this, I can rewrite it like this. In this sense, they are basically equivalent up to this factor of square root of g. However, t mu nu has two indices. And if I try to write the divergence of t mu nu in this way, I find that, okay, with respect to the first index, I indeed can rewrite this in this form. So this would be the first term with a connection can be combined with the partial derivative in this way. But there is another term. Okay, and this term has this form. Oops, sorry, this is I'm writing the connection. Now this is symmetric, this is also symmetric, and this doesn't vanish. So if I say that this is equal to 0, this doesn't mean that this is equal to 0. So this cannot be understood as a conservation law, although often people refer to this law as a conservation law. And well, in fact, we have no reason to expect that the energy momentum tensor, the gravitational energy momentum tensor, is conserved by itself, because matter, the matter which is described by this energy momentum tensor, whether they are fundamental fields or something else, is coupled to the gravitational field. And now, well, the energy of this field cannot be conserved separately of that of the gravitational field. Okay, there is an interchange of energy between matter fields and the gravitational field, and this only takes into account the matter fields. So the energy of the matter fields separately is not conserved, because there is an interaction with the gravitational field. There is a problem to find a complete general conservation law for the total energy momentum tensor, because, as we have stressed, there is no energy momentum tensor for the gravitational field itself. So you cannot say that the total energy momentum tensor of matter plus gravity is conserved. Only in an approximate way, in the weak field approximation, as we will see, you can say something like this, but never in an strictly an exact way. Okay. So the question now is, if this is not a conservation equation, it is some sort of identity, and where does this identity come from? Okay, the result that I'm going to advance is that this identity is related to invariance under general coordinate transformations, and it is related via the second-order theorem. Okay, the second-order theorem always gives us relations between equations, some sort of identities which are satisfied, and this property or this identity is related to that, and we are going to prove this. So let us consider infinitesimal general coordinate transformations, which are given by an infinitesimal vector. I can decompose this into an infinitesimal parameter epsilon and a general vector, but it is enough for our purposes to do it like this. And now let us consider field theory, okay, for instance for a scalar field that also includes the metric as a background field. Okay, and let's if this theory satisfies the principle of general covariance, then we know that under these transformations this action should be invariant. Now this is just the consequence of the principle of general covariance. So the question is what are the implications of this invariance, and we are going to follow essentially the same path that we followed when we proved the first Noether theorem and so on to find the consequences. So we if this theory if this theory has the form oh my god d for x and then a Lagrangian density, then this variation is first of all the variation of this volume element times L plus d for x, this variation times L. And here I haven't used this tilde because, well, it is the variation of the coordinates, so there is no distinction between what I call the total variation and the variation at a point with tilde and without tilde, but here we really mean the variations with the tilde. Okay, and I know that operating with this tilde is always complicated because we know that delta tilde does not commute with partial derivatives, so we replace the delta tilde by delta plus the transport term using the general relation delta tilde epsilon equal to delta epsilon plus epsilon mu partial mu, understood as operators on whatever fields we have, and in particular the Lagrangian density. Okay, I am going to do that, but first remember what was the transformation of d for x. We did this in another video in the past, and the result was that it was d for x times this divergence of epsilon mu. Okay, this takes care of the first term, and the second term, which has this d for x here, and that I take as a common factor, is just this plus the transport term. Okay. Now I can combine these two terms into a total derivative. And this delta epsilon L, I vary L as usual. So first is the variation, the partial derivative of L with respect to phi, delta epsilon phi, plus the partial derivative with respect to partial mu phi times delta epsilon of mu phi. And we assume that, and sorry, there is of course dependence on the metric, so I need to add this term. Okay, and I don't need the partial derivatives of L with respect to partial derivatives of G, because at least in this case that we are considering, which is the scalar field theory, there are no covariant derivatives, so there are no connections, and then no partial derivatives of G. Otherwise, I would have to take care of that as well. So now I need to know this delta epsilon phi and this delta epsilon d mu phi. This is something that we studied when we studied the scalar field, and under this kind of transformations we have this. Remember that this basically this follows from the property that the scalar is invariant. Then the variation of the partial derivative of phi, since this variation commutes with partial derivatives, okay, it is not the delta tilde epsilon does not, but this one commutes, then we have this, and then we just compute the partial derivative of what we have above, and we get these two terms. Okay, finally we need this variation. Okay, this is a bit more complicated to get, but you can do it in the same way as you do it with this, similar, in the following sense. Okay, this is the transformation, after all, of covariant vector field, or a one form, which is this one here. Okay, basically you expect a general term like this for any covariant tensor, but you expect a term like this for every index, every covariant index. This means that what you expect, and if you want me, I can try to prove this without making use of complicated things. Okay. Otherwise, you can just trust me on this. There will be this general term. Here I need a different index. And then a term like this. Okay, when I consider the first index, and another term like this when I consider the transformation of the second index. Okay, there is a much better way of writing this expression, which is not only compact, but that leads to an equation which can be solved, and you will see many times. Okay, so let me try to write it for you. Well, let me do first the following. I replace all the derivatives by covariant derivatives, and I am going to show that this is possible because all the terms that I have to add, which are terms proportional to the connection, cancel. So this is really this, but I need to add two more terms. Okay, so far nothing has happened. Now I write this covariant derivative and I subtract the term mu sigma, and let me call this rho epsilon rho. And for the other one, similar, but with mu and nu interchanged. Epsilon rho, sorry, and this one is multiplied by g sigma nu, and this one by g sigma nu. Now observe that this term, okay, is equal to this term, but comes with the opposite sign. I need to use the fact that the connection is symmetric, so instead of rho mu, I have mu rho here, epsilon rho is multiplied here, this comes with a minus, this minus a minus, this comes with plus. Well, the conclusion is that these two terms cancel, and the other one, because it is the symmetric in the interchange mu nu, also cancels. So the first thing is that I can replace these partial derivatives by covariant derivatives, and because I am using the Levi-Civita connection, this term vanishes automatically, and I am left with these two things, epsilon sigma, g sigma nu, and they interchanged. Okay, I can now lower the indices using the metric because the connection is metric compatible, and then I get minus nabla mu epsilon nu minus nabla nu epsilon mu, or as you will often see it. Okay, remember this result because we will use it many times in what follows. So I take this, this, and this, and I bring it to the variation of the action, and I get the for x. Well, we have the first term is this total derivative, epsilon mu L. Then we have the partial derivative with respect to phi and the variation with respect to epsilon of phi. So there is a minus sign, and this term, this is what I am using. Okay. The next term also carries a minus sign, partial L, partial, and phi, and whatever is inside of this. And finally, the term with the variation of L, partial derivative of L with respect to G mu nu, and this also carries a minus sign and a factor of 2, nabla mu epsilon nu. Okay, and this is the result so far. Now, as usual, we want to get rid of derivatives of the parameters or the variations. Okay, and here we have only one. So I am going to integrate by parts all this term. This means that I get one more term in the total derivative. Okay, that comes with a minus sign, and which is partial L, partial nu phi, and partial nu phi, and epsilon nu. Okay. Then we have the term that we get by integrating by parts, which is partial mu acting on this times partial nu phi, then the last term phi partial nu phi, and okay, I am always forgetting that this comes multiplied by epsilon nu, and then this term here, which is minus partial L partial mu phi partial nu phi epsilon nu, and this term okay, the first thing that I notice is that these two terms, the second derivatives of phi, cancel. The second thing I notice is that I have forgotten this term as well. Sorry. It's minus partial L partial nu phi. Okay, another thing is that this partial derivative with respect to G mu nu, okay, this is basically with G mu nu, and since the indices of G mu nu of the metric are down, this is 2 times divided by, sorry, the other way around, is the square root of G divided by 2 T mu nu, okay, the gravitational T mu nu, which in this case coincides with the canonical one, so I'm not going to make any distinction. So let me come here, and first of all, I reorder a bit this total derivative. There is epsilon nu, a common factor of delta nu mu L minus partial L with respect to partial mu phi partial nu phi. Okay, and remember that this is going to be essentially the canonical energy momentum tensor. This is why I write it in this way. Then we have the terms which are proportional to epsilon nu partial nu phi. And which up to the sign, okay, they give me the equation of motion of phi. Finally, I have this term. Let me write it. It is minus square root of g t mu nu nabla mu epsilon nu, and I am removing the symmetrizer in the lower indices because t mu nu is symmetric and I don't need it. Okay, next step. The next step consists in integrating by parts this term, because as I said, we want to remove all the partial derivatives or all the derivatives of epsilon nu, or the parameter of the transformation. And okay, this means we are going to collect another term in the total derivative. This term is minus square root of g t mu nu plus, sorry, with epsilon nu, but let me take epsilon nu with index up as a common factor. So I have this delta nu mu L minus partial L partial nu phi. Okay, then we have minus epsilon nu partial nu phi delta S delta phi. And finally, well, we integrated by parts, but we still have to consider this last term. So it's nabla mu square root of g t mu nu epsilon nu. Okay, this covariant derivative, okay, this is a tensor density, but the covariant derivative we have also defined it in tensor densities. And what we saw is that when we use this covariant derivative, which also takes care of tensor densities, this the square root of the determinant of the metric is covariantly constant. So this means I can take this square root of g outside of the covariant derivative, and I can remove the parentheses, and this is what I have. Now the next thing to notice is that okay, these terms cancel. This is the canonical energy momentum tensor up to this square root of g, and it coincides with the gravitational energy momentum tensor. Okay, there is the square root of g and the sign, so this all this term cancels identically. And now at this point is where I have to warn you that if you try to do the same for a vector field, you will get into trouble, because you know that the canonical energy momentum tensor first of all is not symmetric. It is not gauge invariant, but it's not even symmetric, since the gravitational energy momentum tensor is derivative of the action with respect to the metric, which is symmetric, then it is always symmetric. You cannot cancel something symmetric with something which is not symmetric, and this cancellation will not take place. If you use something a bit more sophisticated, you take into account some peculiarities of the vector field, then you will get this cancellation, but it is more complicated. This is why I am restricting myself to the scalar field in this example. But this can be proven in general. It is not a mystery, okay? So it's just that it is a bit more complicated to do. You will get this cancellation, and in the end, you find something which is proportional to epsilon nu. Well, depends on if we want to write it up or down. Let's write it down. And you have the divergence of the energy momentum tensor minus partial derivative of phi delta S delta phi. Now we have assumed from the beginning that this action is invariant under these transformations, because we just take actions that by construction satisfy the principle of general covariance and are invariant under general coordinate transformations. This is what we have assumed from the beginning. So we know that this is 0, and this is 0 for any epsilon. The conclusion is that this nabla mu t mu nu is equal to, well, let's write it in a different way, like this. Okay, and this is the identity. Sorry, I forgot to divide by square root of g when I took a common factor square root of g here, so the identity is exactly like this. These are tensors, and what you have on the right hand side has to be a tensor. And since the action always includes a square root of g, then unless you divide, you don't get tensors. So this is what you prove, that is always satisfied. And you will prove something like this if you consider a theory with more fields. You will have a linear combination of the equations of motion of the different fields times derivatives of those fields. So it's always the same. It's completely general, and the consequence is that if you are on shell, if the equations of motion are satisfied, the equations of motion of the fields, this vanishes as you expect. Okay, so although this proof has been made only for a scalar field, you can trust me that it can be generalized to other fields, and the consequence, the result, is that the gravitational energy momentum tensor has the property that its divergence, its covariant divergence, vanishes on shell. And while we cannot say that this is a conservation law, well, it is related to it, because it certainly reduces to a conservation law when we consider the fields in a trivial gravitational field, so there is no interchange of energy with the gravitational field. So we set the metric to Minkowski, and this will be a standard conservation law. Well, it is a property that you have to take into account, and that follows, it's something that follows, an identity that follows directly from demanding invariance of the action under general coordinate transformations. Okay. So although I'm not going to prove this general result for in this way for the electromagnetic field, I can prove that the energy momentum tensor that one obtains by this prescription for the electromagnetic field is indeed is divergence free on shell. Let me first compute this gravitational energy momentum tensor. Remember, what we have to do is to vary the action with respect to the metric, and remember that the action, so here I'm not going to vary the vector field, and the action is just the square root of g minus 1/4 f squared. Okay, and this f squared, when we expand it, something like this: g mu alpha, g mu beta, f mu nu, f alpha beta. So this is what we want to vary with respect to the metric only. And as usual, we vary with respect to the metric, the inverse metric, with the indices up. So we get a first term, which is the variation of the square root of g. And remember that this was minus half the square root of g let's say rho sigma delta G rho sigma, multiplying the rest, which was minus 1/4 of f squared. Now I have another term. It has this factor minus 1/4, and then clearly this is symmetric in this 2g, so it will give me a factor of 2. I only need to vary one of them. And let me write rho sigma just to make it coincide with the other variation, so I can take a common factor. Okay, so now this will be rho nu, and this is sigma beta. Okay, so first I have a factor of square root of g, which is a common factor. I also have this factor of delta rho sigma, and the first term is 1/8 g rho sigma f squared, and the second factor, the second term that I have here is minus a half, and I have f rho beta f sigma beta, and I have used this to raise this index and call it beta. Okay, now I know that this is the variation of S with respect to rho sigma, and then the energy momentum tensor, the gravitational energy momentum tensor of the electromagnetic field with the indices down, because I am varying with the indices up, which is given by minus 2 divided by square root of g delta S delta G rho sigma with the indices up, is first I write this term because with the minus 2 gives me a positive number, beta f sigma beta, and then the other term, which is minus 1/4 g rho sigma f squared. If you set g equal to eta, you will get this Bell-Infante energy momentum tensor, which we obtained from the canonical one by adding certain improvement terms that allowed us to recover gauge invariance, and which at the same time made it symmetric. At the moment we said, okay, this is a very good energy momentum tensor because this is the one that will couple to gravity, and this is how we are recovering that result. Now, if we try to prove the same property, that the divergence of this energy momentum tensor is 0, okay, let me write this as f mu alpha f nu alpha minus a half g mu nu f squared. Okay, the first term that I get is clearly, it has an alpha, is clearly the Maxwell equations that we have derived before, so this will vanish on shell. The second term comes like this, and okay, you have mu alpha. I am writing the first term in the second position, but it doesn't matter. Here, sorry, this is 1/4 minus 1/4 and nabla nu f squared. This gives me a factor of 2, and for instance, let me write this as mu alpha and mu alpha. Okay, so I get a common factor f mu alpha, and here I write mu alpha minus 1/2 of nabla nu f mu alpha. Okay, because since this is contracted with mu and alpha, which is antisymmetric, this is automatically antisymmetrized. And in particular, I can write it expanding this as 1/2 of nabla mu f nu alpha minus 1/2 of that. And then I take 1/2 as a common factor, and I write this nabla mu f nu alpha minus nabla alpha f nu mu minus nabla nu f nu alpha. And okay, just to make this more explicit, let me interchange these two indices. So I get a further sign of minus, a further minus sign, which I put here, so I get rid of them. And just trying to make this, to write this in a more recognizable way. Because you see that now in this expression, the indices have been permutated cyclically. I can make this more explicit by taking, by writing this if you want in this way. So I take a metric like this. So and this would be f alpha beta plus nabla alpha f beta mu plus nabla beta f mu alpha. And you see that you get this term by taking mu here, and you get this one by taking alpha here. So it is cyclic permutations, and this is nothing but 3 times this is completely antisymmetrized, and because of the Bianchi identity, well, this is the Bianchi identity that tells you that this is identically 0. Okay, this is 0, but we have used the Maxwell equation here, so this is 0 on shell as expected. In fact, what you get is the equation of motion, okay, just like here. In the general result, you get the equation of motion. Here it was delta S over delta phi times the derivative of the field. And essentially, this is what you get, because f is derivative of the field. But the whole result is gauge invariant, and this is what you expect. And now that we have studied, first of all, how to couple these fields to background metric field or a background gravitational field, we have studied the equations of motion or the variation of the action with respect to the fields. We have also studied now what happens with the variation of this action with respect to this metric field. We can put everything together and think of the general situation. In the general situation, what we expect, although we don't have it yet, is that the whole action will have several terms. A term that we call is graph, and that basically contains only the metric, and which will give you the dynamics of this metric. Okay, and this is the thing that we will try to determine in the next lecture. Well, sorry, in the next section and in the next video, in fact. It will also have another piece that we can call matter, and which is field theory, but coupled to this gravitational field. Okay, and because of the arguments that I gave you before, this term will give you the source for this term. Okay. Now let's try to find first what are the properties that this has to satisfy, because the variation with respect to the metric of this term, we know what property satisfies. Is this divergence free if the equations of motion of the fields phi of the matter fields are satisfied. So what happens for the other one? Okay, let's just consider the variation of this action with respect to the general coordinate transformations, infinitesimal general coordinate transformations that we studied before. Clearly, this action has to satisfy also the principle of general covariance, so this has to be 0. And now Okay, making the argument really short, because we don't know what is the form of this action, but we know that the result of varying will be something like this, plus total derivatives. Okay, just by definition of how we find the equations of motion. Now we know that this is minus 2 times the symmetrized derivative of epsilon nu, and we can integrate by parts. If we integrate by parts, we get a total derivative with more terms, and then a factor of 2 mu delta S gravity delta G mu nu epsilon nu. Okay, now there are different ways of ensuring that these total derivatives cancel. One way is to really perform the integral and impose some boundary conditions on the epsilons. You still have many different epsilons that satisfy those boundary conditions, so you can get rid of them, and then for all those epsilons, which are still quite a lot, this will be 0, which means that whatever these equations of motion of the gravitational field are, when it is uncoupled, because we are only considering the free part, if you want, they have to be divergence free, but now off shell. Okay, and this is an example of what we call the gauge identity or Netter identity. It is an identity that relates equations of motion, which in principle you thought that they were independent, okay, and this identity tells you that they are not. And they are not off shell. It's not that for some particular solutions they give you, no. In general, they are there is a dependence between them, and this is a consequence of the fact that there is gauge symmetry, and that you can eliminate some of these G mu nu. The metric clearly is a redundant description of the gravitational field, but you could eliminate some components by performing general coordinate transformations and so on. You don't do that because then you lose general covariance, which is a symmetry principle that helps you to construct all these theories. But you have to be aware that in principle it is possible. You have a very, very redundant description of the gravitational field, and the consequence is this very important identity that has to be satisfied. But then if we go back to the general action, then okay, what happens now is that the complete equations of the gravitational field, including sources, including matter fields and so on, will be these equations plus the variation of the matter action with respect to G mu nu, and this is well, this part of the left hand side, if you want, of the equations of motion of the gravitational field, plus a half of the square root of G of the gravitational energy momentum tensor of the matter fields that you have. And on shell, by definition, this has to be 0. Well, you would probably want to write this in this way. And then if you take the covariant divergence of this, you know that this has to be 0, okay, always. And because this is an identity which is true off shell, and okay, the conclusion is that you have that this has to be 0 by consistency. Otherwise, you cannot couple matter to gravity because this is divergence free, so this side has to be also divergence free. Now you know, because we just proved this, that this is essentially this up to 1 of the square root of g. This means that this forces you to have 0. So the consistency of all this picture implies that the equations of motion of matter have to be satisfied. This is a very important conclusion. So if the principle of general covariance is satisfied, this is the first assumption, so we have an action for gravity which is general covariant, and we have an action for matter coupled to the gravitational field which is also general covariant. Then the equations of motion of the gravitational field, which are this, okay, it doesn't matter which theory you are in as long as it satisfies the principle of general covariance, then they essentially imply the equations of motion for the matter fields. This should remind you something. When we studied fluids, you could recover the equations governing the fluids, which could be the equations of motion of the fluid in a sense, by imposing the conservation of the energy momentum tensor. Now the situation is a bit more complex. This is not really a conservation law, it is a consistency condition, which is implied by general covariance, but the conclusion is the same. By imposing this consistency condition, demands or implies the equations of motion of the fields. If you have here a linear combination, you have more fields, and you have here a linear combination of the equations of motion of different fields times derivatives of those fields, well, it is more complicated to conclude that each of them is satisfied separately, but still this is a quite important constraint that you have to be aware of, because it is very useful. And in fact, when we deal with fluids in the context of general relativity, this is the only equation of motion that we can have. Okay, it will be derived precisely from this consistency condition, which I stress again, it is not to be seen as a conservation law. From the practical point of view, it also means that in simple cases, I don't need to worry about solving the equations of the matter fields if I solve the equations of the gravitational field. You may wonder why this is so. I mean, because these look like logically independent things. I mean, you have the gravitational field on one side and you have matter fields on the other side, and why should the equations of one imply the equations of the other? However, you have to take into account that basically the gravitational field knows everything about energy and the energy of the fields. You cannot have a consistent gravitational field that solves the equations of motion of the gravitational field, whatever they are, if the balance of energies in the matter sector is not right. And well, you have probably solved many problems in your degree in physics, or maybe even in high school, by reasoning in terms of energy, which is much simpler than just solving equations of motion and finding accelerations and so on. Basically, you see that the balance of energy determines the dynamics. So if the gravitational field knows everything about the balance of energy, it knows indirectly a lot about the dynamics. And this is a very, very, very important physical fact about the gravitational field. With this, we are essentially ready to now go out and try to find, a good candidate for this action of the gravitational field, and from this action the equations of motion. Okay, this part of the equations of motion, because after all this discussion, it is clear that the right hand side of the equation, the The right-hand side of the equations of motion is determined by the energy momentum tensor of all the matter fields. So all we need to determine now is the left-hand side. Okay, and this is what we are going to do in the next video.